Well, hello and welcome again to our journey into number theory, and we're moving now on to the sums of integer squares. So we've just finished looking at quadratic reciprocity. I should mention that in addition to quadratic reciprocity, one also can have a theory of cubic reciprocity and biquadratic reciprocity, and indeed there are general reciprocity laws as well, but these would take us well beyond where we need to go in this section. So sums of integer squares, we observe that the numbers 8 and 90, for example, can be expressed as the sum of two squares. So for example, 8 is 2 squared plus 2 squared, and 90 we can write as 3 squared plus 9 squared. On the other hand, if you try and play around with 35, you discover that no matter how you try, you can't write it as the sum of two squares. You actually need 3 squares. It's 5 squared plus 3 squared plus 1 squared. And even 3 squares is not enough for the number 28. You need to write it as 5 squared plus 1 squared, 1 squared, 1 squared, or there's two representations, 3 squared, 3 squared, 3 squared, and 1 squared. But you can't get away with less than 4. So in this section we're going to have a look at what's happening here and try to predict the minimal number of squares that are required to represent a given positive integer. So as usual, we're going to begin by restricting ourselves to primes. Primes are always the easiest thing to deal with in number theory, and so we start at the primes. Now, since the squares modulo 4 are only 0 and 1, so if you square 0, 1, 2 and 3, you only ever see 0 and 1, we immediately see that a prime congruent to 3 mod 4 is not the sum of two squares, because if you only got two squares, then you'll either get two zeros, a 0, 1, or a 1, 1, and that'll only give you 0, 1, or 2, and you won't get 3. Now this, of course, it turns out to be true for any integer n, not just primes. Now, what's the situation for 3 mod 4 primes? You can't write those as the sum of two squares. So, for example, 7 is not the sum of two squares. The situation for primes congruent to 1 mod 4, however, is very different. You can take a number like 5, of course, which is a 1 mod 4 prime, and write it as 2 squared plus 1 squared. And in fact, the following theorem tells me I can always do that for any 1 mod 4 prime. This is a lovely proof. There are many proofs of this. This is, I think, one of the nicest proofs. It uses, in fact, the pigeonhole principle. So it says, suppose we've got a prime p congruent to 1 mod 4. Then we can express this as the sum of two integer squares. So, for example, I mentioned 5. You can take 17, which is 4 squared plus 1 squared, and so on. So any 1 mod 4 prime can be expressed as the sum of two squares. So 29, for example, is 5 squared plus 2 squared. Now we're going to use, again, a couple of points here. We see again that the prime's bifurcating into this 1 mod 4, 3 mod 4 scenario. And essentially the fact that the 1 mod 4 primes can be written as the sum of two squares essentially is equivalent to the fact, or certainly connected to the fact, that you can find the square root of minus 1 mod p if p is a 1 mod 4 prime. And indeed, that's where we're going to start. So by the corollary to Wilson's theorem, there is an x in Zp, because p is a 1 mod 4 prime, whose square is minus 1 mod p. We're going to take the set S, consisting of the numbers 0, 1 up to, you take the square root of p and take the floor, the square root of p. And in this set, all these numbers, and I also look at all numbers of the form a plus bx. So x is this thing here whose square is minus 1, and a and b are elements of this set. So we might take, for example, 2 plus x. Anything in this a and b from this set, and x with this property. Now let's just see what we can say about this. So there are square root of p, take the floor, plus 1 squared, which by the way is bigger than p if you square it out, because this gives you p plus 1 plus something. Values for ax plus b. because you've got to include 0 here. So you've got the floor of p plus 1 numbers in here, choices for x, and the same number of choices, sorry, for a, same number of choices for b, so that many choices for this a, for these ax plus b's. So modulo p, by the pigeonhole principle, that 2 of these, there are more here than there are values of p, so 2 of these must be the same modulo p. So there has to be an little a plus little bx congruent to capital A plus capital Bx modulo p, where the for some a and b, for some little a, little b, capital A, capital B, and this pair, as an ordered pair, have to be different. These have to be different. Hence, if I now subtract that, if I now rearrange that equation, I get little a minus capital A is congruent to little b minus capital Bx mod p. And now comes the little trick. I'm going to square both sides of this, remembering that x squared is congruent to minus 1 modulo p. So this gives me little a minus capital A squared is congruent to minus, that's the x squared, capital B minus little b squared. And I can take that on the other side, and then I have, so this is modulo p. So that means this plus this has to be 0 mod p, that is, it's a multiple of p for some integer c. Now the name of the game, I want to try and show this c is 1. So I now measure the distance between little a and capital A. Well, both of these came from that set S, and so there, the difference between these in absolute value has to be less than root p. Same for the b's. And so when I plug those inequalities into here, I get that squared plus that squared has to be less than p plus p is 2p. On the other hand, this is cp, and that means cp is less than 2p, so c has to be 1. C clearly is not 0. So c is 1, and that means then the result follows. So I now have p is the sum of 2 squares. That's a very nice, cute little proof just using, and it shows also the close connection between the fact that you can write these 1 mod 4 primes as the sum of 2 squares and the connection with being able to take the square root of minus 1 modulo p. By the way, of course, 2 is 1 squared plus 1 squared, so this now deals with all the primes. So if you've got the prime 2 is trivially the sum of 2 squares, a 1 mod 4 prime is always the sum of 2 squares, and indeed we'll see shortly that it's unique. It is in fact unique up to order and perhaps putting in some minus signs in front, so you could write this as minus 1 squared plus brackets minus 1 squared. So up to signs and order, then every 1 mod 4 prime is in fact uniquely the sum of 2 squares, and every 3 mod 4 prime is not. Now this simple identity here, which you can get easily using complex numbers in fact, you simply take the square of the norm of a plus ib times the square of the norm of c plus id, and then you multiply the a plus ib, c plus id, and square the norm or the modulus, and this thing just falls out. Anyway, apart from that, you can just check by expanding everything out that this is a true identity. Now what does this tell me? It says, well, if I've got a number which is the sum of 2 squares and another number which is the sum of 2 squares, then I can multiply those two numbers together, and the product is also the sum of 2 squares, and that tells me explicitly how to do it. So this shows the product of two numbers, each of which is the sum of 2 squares, is also the sum of 2 squares. And that enables us, with a little extra work, I'll leave you to perhaps fill in some of the details, to be able to argue now that you take any positive integer n and you factorise it in this way. That is, if it's even, you take out a 2. So you get 2 to the epsilon. So epsilon's either 0 or 1. It'll be 0 if the number n is odd. It'll be 1 if it's even. You pull out any square factor that you can. You take out the biggest square factor out of n, and you're left with a product of primes. only to the power 1. So this is a slightly different to our normal way of prime factorisation. You pull out a 2 if there's 1 there, you take out the biggest square factor, you're left with a product of primes, and so each of these pi's are primes. Then this theorem says that n is the sum of 2 squares if and only if each of these primes has to be a 1 mod 4 prime. Each of these primes has to be a 1 mod 4 prime. And that's the complete characterisation then of being able to write numbers as the sum of 2 squares. Now we can, I'll show in the example how we can use complex numbers here to actually do the arithmetic, which is very nice. So for example, we're going to take the number 5525. So let me firstly just mention that this number of course is odd. So when you take this factorisation, epsilon will be 0. It's got a factor of 25, so you pull that out, and you're left with, after you factorise what's left, you're left with 13 times 17. And both of these are 1 mod 4 primes. So I'm going to try and write 1525 as the sum of 2 squares in as many different ways as possible. Okay, so here it is. Here is our number. So we took out the square factor, we factorised what was left uniquely into a product of primes. Both of these are 1 mod 4 primes. And so we know that individually I can write each of these ones as a sum of 2 squares. So I write 13 as 3 squared plus 2 squared. Now I can write this using complex numbers, which is very nice way of doing things. So I can write this as the square of the modulus of 3 plus 2i. And by the way, I can also write it as the square of the modulus of 2 plus 3i. So notice you can do this in 2 different ways, and I could have put some minuses in here as well. I could have put plus and minuses here, but I'll just do these two. 17 similarly is 4 squared plus 1 squared, so I can write that using modulus as complex numbers. And by the way, notice also this 25, which is 5 squared, I can also write as the in this way. I can write it as the square of the modulus of 3 plus 4i or 4 plus 3i. Again, I could put minuses in here, but these the pluses and minuses turn out to only differ by a unit, that is plus or minus 1 plus or minus I from all the other ones that I've got there. So you don't get anything new by multiplying by units, that is plus or minus 1 plus or minus I. Okay, so here we go. We take this number n. Firstly, it's 5 squared times 13 times 17. So there's 5 squared. 13 is 3 plus 2i modulus squared. 17 I take as 4 plus I modulus squared. I'm going to multiply these together using the properties of the modulus. And I multiply these complex numbers together, I get 10 plus 11i. So you get 12, you get 10 plus 11i modulus squared. And now I go back and work out the modulus squared. So this is going to be 10 squared plus 11 squared. And I can take the 5 inside that and write that as 50 squared plus 55 squared. So there's one way of writing 5,525 as the sum of 2 squares. That used this representation and this representation. Now I'm going to use this one. I used that one and that one. Now I'm going to use this one and this one. So again, I take the 5 squared out. I keep that one alone and use the other one here. Use the 1 plus 4i. Now, again, you multiply these out. We get minus 5 plus 14i after you multiply out. And again, you can then say this is 5 squared plus 14 squared. Multiply by 5, you get 25 and 70 squared. There's the second representation for this number as a sum of 2 squares. Now, I can also now start using the 25 in this form. So I'm going to take this one and I'm going to use this product that we got from here, the 10 plus 11i. So I'll do the same thing again. I multiply these out. I expand this out. I get minus 14 plus 73i. And that gives me 14 squared plus 73 squared. and there's another representation of the number as the sum of two squares, different to the ones we've had before. Similarly, I can take 3 plus 4i, and I'm going to use this one for the product of these other two, and multiply it out, you get this. So that gives you another representation, 71 squared plus 22 squared. I can also now, I took 3 plus 4i, and now I can take the other one, 4 plus 3i, and do exactly the same thing. And so I get 7 squared plus 74 squared. And I can do exactly the same thing here, multiply these out by taking the 4 plus 3i times the other one, and I get 62 squared plus 41 squared. And there are the 1, 2, 3, there are the 6 representations of 1525 as the sum of two squares, using this lovely idea from complex numbers, just complex arithmetic. And notice we could of course only do this because these numbers here were 1 mod 4 primes. Well, one can look at other representations of numbers, so which I'm not going to deal with here, but you can look at other forms of representations by squares. For example, you can try and write a prime p as a square plus 3 times a square. And it turns out that you can do that if and only if p is a 1 mod 3 prime. Or you can try and write it as the sum of two squares minus the product of those two numbers. And again, that turns out only to be able to be done if p is a 1 mod 3 prime. And there are other representations one can do. Look at a square plus 5 times a square, and so on. Plenty of these stuff in lots of the number theory books. This is as much as we'll do with the squares here, sum of two squares here. Now we come to the question of the number of representations, so that we saw that there were 6 different ways of representing 5525 as the sum of two squares. So we now turn to the question of how many representations there are. And so we'll count a representation such as 5 as 2 squared plus 1 squared as having in fact 8 representations, because you can then you can write this as plus or minus 2 squared plus or minus 1 squared, or you can turn them around the other way and write it as plus or minus 1 squared plus or minus 2 squared, and if you count all that up, that gives you 8 different representations. It turns out to be convenient to look at it this way. And if you want the number of essentially different representations, that is ignoring the order and the signs, well, that's okay, you can just divide by 8. So, I'm just going to state again without proof. You can find the details of these things in various books. So I'm going to state the following theorem, which goes back to, let me begin up here. So I'm going to write n of n to be the number of representations of n as the sum of two squares, counting sign and order. So for example, n of 5 is 8. We can write 5 as the sum of two squares in 8 ways, counting all the different signs and the orders as we did above. So I'm now going to introduce this interesting function here. This is f of n is d1 of n minus d3 of n. So d1 of n is the number of positive divisors of n of the form 4k plus 1, and d3 of n is the number of positive divisors of n of the form 4k plus 3. Finally then, we have the following theorem, which goes back in fact to Jacobi. Using the above notation, for any positive integer n bigger than 1, this n of n, the number of ways of representing n as the sum of two squares, counting sign and order, is 4 times this function f of n that we saw above. So if n is a prime of the form 4k plus 1, then n of p is just 4 times f of p, and f of p, of course, will be just 2, and that'll give me 8. So and the reason this is 2, of course, is that it's divisible by 1, of course, and it's a prime, so it's divisible by itself. So f of p in this case would be 2. That gives me 8. Now that's interesting, because that now tells me that, ignoring order and signs, I divide this number by 8, and it tells me there's only one way to express a prime as the sum of two squares if we ignore order and sign. And that follows immediately from this little theorem here. So in the example above, when I looked at 5,525, remember we factorised it this way. Every factor of n is congruent to 1 mod 4, and there are going to be 12 such factors. Hence the number of representations is going to be 4 times 12, which is 48 by this theorem. And then I've got to divide this by 8 to get the number of essentially different ones. And that gives me 6, in which order and sign are unimportant, and that's exactly what we saw above when we did it by hand. We saw there were 6 representations of this number as the sum of two squares. In the next section, we'll move on and have a look at Pythagorean triples.